Hey guys, in today's video we'll be straying away from our normal optics topics and talking about a recent study that I did into bending loss in optical fibers. And I just want to share with you my process, research, and some findings that I made. So my hypothesis was that at a fixed radius and wavelength, bending loss in an optical fiber would increase linearly with the number of turns, while loss per turn across different radii, bending radius, would increase exponentially, and higher wavelengths would actually make these optical losses larger. And my justification was, so imagine this gray area as a fiber, and the light is propagating from the left side of the screen to the right side of the screen. You can see in the middle there is kind of like a wave guide with the power pointing to the right. And I thought that, okay, if the wavelength was longer, then there would be more, the wave would be longer and more of the power would be lost outside of the waveguide. I also thought that with a sharper radius, the loss wouldn't be linear, but actually exponential. And yeah. So I just designed an experiment, and it took me a while to find a reliable way to conduct it. What I decided to do was wrap an optical fiber around mandrels of different radii, like in the image shown, and record it using optical fiber testing kit, which I'd shown off in the previous video. So you can see that here in our setup, I have a light source on the left and a power meter on the right. After multiple trials, I decided that it was important that these were taped down, as well as a part of the fiber directly after the connection point between the light source and the cable, or the power meter and the cable as well. And this is to prevent connection issues, as I found that sometimes wiggling or movement around the connection ports would cause fluctuations in measurement accuracy. So to reduce that kind of noise, even between trials, I would always keep those taped down. Another thing that I found that was that keeping the power of the power meter or the light source constant was important. So always switching fresh batteries between trials and days of testing was very important in order to keep consistency. In the middle, I would use a mandrel, and I would wrap different amounts of paper around the mandrel to increase the thickness of it. So I think the smallest we had was around 7.4 millimeters radius. So I would wrap the coil the optical fiber around the mandrel to create bends, and I would record power and loss after a certain amount of coils, like 5, 10, 15, 20, and 25 coils. And so I plotted some of the data I found into charts. And the first two you see here is our linear graphs, because which supports our hypothesis of loss increasing linearly with the amount of turns. So dBm is a unit of measurement for power loss, or just power, absolute power, in optical fibers. And more negative values correspond to larger losses. And you can see on the left, the 1310 graph, I could only test 3 different radius, because any other radius that was bigger, or that was bigger, it was just not that sensitive, and it would not pick up enough noise, or it wouldn't pick up enough loss to that would be outside, just like typical noise. And you can see that already, even with the 10.925 millimeters, we're not losing much. You only really see some major loss in the 7.4 millimeter radius. And you can see it's very linear, which supports our hypothesis, and it also proves that my recording of the data was tested under ideal conditions. The regression constants are very close to 1, which is always good to see. Taking a look at the 1550 graph, there is a lot more variability between the wavelengths. More wavelengths were tested, and even at the bigger wavelengths, it's hard to see much loss. But you can see at the 7.4 millimeter radius, there is almost 50-ish decibels loss compared to what we started with, which is around like 4 dB. So it's quite tremendous, the amount of loss, which just proves how sensitive 1550 is compared to 1310 because of it being harder to confine the light within the fiber as the wavelength grows larger. Another graph that we could take a look at is the average loss per turn values at different radii. So, and you can see it's clearly an exponential dependence, especially for 1550, as you can see. Yeah, which proves our hypothesis that as radius increases, the amount of loss per turn should not increase linearly, but rather exponentially as you decrease the radius. To further validate this, I plotted a log linear graph of this where we plotted the natural log of loss per turn. And if the log of the exponential graph would be linear, then we can prove that it really was an exponential dependence. You can see at both 1550 nanometers and 1310 nanometer wavelengths, regression constants are very close to 1 again, within 0.03, which proves clear exponential dependence for loss per turn versus bending radius. So I hope this gave you some insight into how bending radius and wavelength affects fibers, and I just wanted to share my findings. Thank you so much for watching, and I'll see you in the next video.